Good morning. My name is Slade LaCroix, and today we are going to be talking about case study 13.2 in our books. So let's get into the topic of what we're talking about. So, a manufacturing incorporation called Max's Barbecue produces top-of-the-line barbecue tools such as knives, spoons, forks, and etc. These tools are fabricated by a stamping process, resin handles are added, and rivets are used to attach the handle to the blade. But there are a few defects that need to be resolved during manufacturing. So this can kind of give you a visual aid or representation of what they are making. See, this is actually the exact item we're going to be talking about, which are the table knives. So this is a table knife for barbecue, which is a stainless steel stamped blade with rivets going through a resin handle, which is very similar to the ones they're probably making in this case study. So that can kind of help you visualize what type of errors can incur from manufacturing this item. So here's our Pareto chart that I've made. As you can see, I took the top 8 defects and I put them in order from greatest to least. And you can see that the top 3 are the hit handle, the burn, and the heat induct with the largest number of defects. And then after that, you have the hafting marks, the DD edge, the bad steel, etch, and burrs coming in next. So that is a chart just to give you a representation of how intense some of these defects are. So let's get into question 1. Are there any categories on the chart related? If so, which ones? And the answer is yes. Heat induct and burn defects are similar because they are both reactions to thermal stress during manufacturing. So basically, heat induct, for an example of heat induct would be if you were stamping out a metal part and the metal part heats up rapidly, causing the structural integrity to decrease. And burns mostly come in around sharpening or polishing or anything with friction. And it basically heats the metal up, causes thermal stress, and puts these nasty burn marks on whatever you are making. But notice something that's very interesting here. Both of the 2 defects that are similar are right next to each other. They are actually in the top 3 category. See, burn is number 2, and the other one is in number 3. That is not a coincidence, I don't believe, because both of those are similar and they seem to be large problems in Max's charts. So let's get into question 2. What problems should be addressed first and why? This is a good question. My answer is the hit handle and the burn defects should be addressed first. These are the most occurring defects within the process. But you might be asking yourself, why did I only choose the 2 top defects? Why didn't I choose the top 3 or maybe the top 1? Well, there's actually a principle that's been around for about 150 years that can help you when starting to ask yourself, well, which items do I need to resolve first? And this is called the 20-80 rule. I don't know if you've ever heard of it. It was created by an Italian engineer named Vilfredo Pareto, actually the same guy who made the Pareto chart. So the 20-80 rule basically states that 80% of the problems often stem from 20% of the largest defects. So that is where I got that answer from, is I used the 20-80 rule, and you can see 20% of 8 is 2, which I chose the 2 largest defects present. So that should be the ones that you should start with according to Pareto's principle. So question 3, what types of quality costs will Max incur? Well, the answer is Max should incur appraisal costs, internal failure costs, and prevention costs. So in this question, what it is asking is what types of costs will the company incur while they are trying to solve these issues or after they solve these issues. So let me break down why I chose these 3 types of costs. So with appraisal costs, the company will have to spend money to get new inspections done after the problem is attempted to be fixed. So basically what that is saying is you did an overall inspection at first to be able to say, hey, we have this huge line of defects. Well, you're going to have to do that same inspection after we basically alter the manufacturing process or refine it to hopefully minimize defects. So you're going to have to get your information back to say either yes, it worked or no, it didn't. That's why you'll have appraisal costs in this case. And the next one's internal failure cost. Even if the main problems are solved, it will take time to limit all the problems. So scrap and reworking of defective parts will still take place on a lower scale. Sorry. So basically what this is saying is even though you're going to be solving these problems, and even if you minimize the amount of defects, while you're doing that, you're still going to have defects. You know, it's just living in an unperfect world. When you get these problems even solved 100%, it's still not going to go away in the blink of an eye. It's going to take time to refine every single process. So that's why you're still going to have your internal failure costs, which will be defective parts, but it should be at a smaller level. Then the last one is prevention costs. No matter how many defect problems you solve, you will always have a cost to maintain to basically keep the minimal defect level the same, because parts will wear out and tolerances will loosen over time. So basically what that's saying is you're going to have to keep constant maintenance on these processes to make sure you don't get this same defective issues again, or the number that we have incurred in this situation. So that can be anywhere from replacing dies every 2 months, or lubricating machines more frequently, or inspecting your tolerances on your machines. It's really not limited to anything. It's kind of just another word for general maintenance. So you're going to have to prevent these items from falling back into place, these defects. And that is how you'll have prevention costs. So question 4, what type of prevention costs should Max be investing in to avoid other quality costs, and why? The answer, employee training. This is very important. You could train your employees to better see these issues, to be able to alert somebody to fix them before it gets too out of hand. And better machine tolerances. That kind of speaks for itself. If you have better die tolerances, better fits, stuff like that, better lubrication even, then you can actually minimize your defects by a lot. And improve manufacturing tools. This can kind of go any way possible, because we always need to improve our manufacturing production. And that's with anything. That is a constant improving to make sure that we can either stamp more parts or stamp them more efficiently without defects. Thank y'all for y'all's time, and I hope you enjoyed it.